Hi friends, welcome to my channel. And today I'm going to start lecture 53 on our helicopter dynamics series. And today we are going to develop expressions for lift and drag and the forces which act on the typical blade section. I'm Dr. Ranjan Ganguly. So let's start with the blade section. And now we know the basic nomenclature behind the blade section. So the blade section has this pitch angle theta. And now we are going to focus on the velocity. So we already saw that ut is the tangential velocity, up is the perpendicular velocity, and there's also a component ur which is the radial velocity. So the resultant velocity is u, and we are going to get drag which is parallel to u and lift which is perpendicular to u. And then we are going to resolve this lift and drag into the forces Fx and Fz, which are relative to the plane here, okay, the plane of ut. So essentially that is going to be our job for today, and so let's start with the velocities here. So before doing that, let us define the problem we are dealing with. We are dealing with a rigid blade, no offset hinge, and so there is a rigid flapping beta, rigid pitch theta, and this theta, as we saw before, is given by the pilot. So there is a collective and cyclic control inputs by the pilot which are given to the helicopter rotor. Now the blade element theory assumes that each blade section acts like a wing section or a two-dimensional section, and therefore the influence of the rotor wake is captured completely by the induced velocity up at the section. So we are able to use two-dimensional airfoil characteristics such as CL and CD, lift coefficient and drag coefficient to calculate the section loads. That's why BET is so popular. Now the inflow which is required to calculate the UP term, it can be obtained from various sources. The simplest model we can get is from momentum theory, so that's going to give us the uniform inflow distribution. We can also get from vortex theory, prescribed wake, and free wake theories. So let's now turn to the expression for the velocities. So the three components of the velocity u are given here. So you have the tangential component ut, you have the perpendicular component up, and you have the radial component ur. Now these components are so important in helicopter dynamics that one should completely memorize them. We often write these components in a non-dimensional form by dividing them by rotation speed into radius, hover tip speed. So that's the value here. Now we are familiar with most of these quantities. The lambda is of course coming from the momentum theory or some different theory. And we have some new terms here which we are going to look at. All the terms we typically use in helicopter work we non-dimensionalize. So essentially the velocity terms are normalized with rotation speed into radius. Now we see there is a term involving beta in UP, and this is due to a component of UR which we are going to see. So for example, we see here that there is a UR term like this, and therefore if we take the component we get UR beta is this particular term here. Okay, that's in the direction here, so it contributes to UP. Now each velocity component ut, up and ur has a defined positive direction. Ut is tangential to the disk plane and positive towards the trailing edge. Up is normal to the disk plane and it's positive downwards, and ur is radial and it is positive going out. Now Once we have got these velocities, our objective is to get to the lift and drag. And here in blade element theory, we can look at a blade cross section and we presume it to be a two-dimensional section. So therefore, we can use the formulas. Lift is half rho u square CCl and d is half rho u square CCl, where remember rho is density of air, u is the resultant velocity, c is the blade chord, and Cl is the lift coefficient and Cd is the drag coefficient. So from the lift and drag, we then resolve Fc, Fx and Fr. So of course Fc and Fx we have discussed before also. They are simply obtained by resolution of the forces L and D in the two directions, vertical and in plane of the rotor disc. There's also the force Fr, and Fr is negative beta Fz plus d radial. So these two components are there. One of these are the radial component of the normal force, and the second is the radial drag due to radial flow, which takes place when the blade flaps up. So let's look at the component Fz beta. So if Fz is the force acting in this direction and beta is this angle, then we will see there is a component of the force here which we need to take into account in some cases. So this is the beta related term. So now what we would do is we would take our expression for Fc and Fx and substitute in for Cl and Cd, and therefore we get these expressions here. So you can clearly see here the Cl and Cd have come in these equations, and then we divide Fc by Ac here, Fx by the same value, and we get these two equations. Okay. Also for Fr, we get this equation where we are neglecting the radial drag term. So Fr is completely dependent on Fz, as well as there is a beta term here as we saw in the previous slide. Now of course we can simplify our expression. We don't need to carry all these terms. Let us assume lambda, beta, phi, theta are all small angles. And by small you typically mean around 10 degrees or lower, so that the approximation can be made in terms of the sine and cosine of these angles are small. Now also up by ut, which is phi, is small, and also alpha is small. So with these approximations and also staying in the linear region of the lift curve, we can say that Cl is A into this angle. Now Cd is also constant in this region. We are neglecting stall here, so the angles are all small, and Cd by Cl is much less than 1. So go back and think about Cl and Cd. We already know these shapes are there, and so we are in this region which I have shown by the solid line. We don't want to look at this particular stall region. So this takes place somewhere around 12 to 15 degrees for most airfoil sections. So here also Cd is assumed to be constant. So this does simplify our life. So we can then obtain the blade section forces. So we'll assume Fz is approximately equal to L. Fx is L phi plus d. Okay. So then the expression for Fc becomes like this here. You can clearly see that I'm making some approximations. I'm assuming u is approximately equal to ut, and so I'm getting this simple expression, expanding it out, and so I get this expression here. So this is actually just Fc is half rho AC ut square theta minus ut up. Now similarly I can get expressions for Fx given here, and this part has two components. One of these is dependent on lift, one is dependent on drag. So this is the L phi component coming out. You expand it, you replace this angle by theta minus up by ut, and so on, and so finally you get this expression here. Now important thing in blade element theory is all the expressions come out in terms of the blade sectional properties in terms of CL and CD, and you also now have the lift curve slope coming into these equations. So now we have very compact expressions. So for FR we get a similar term. So already we obtained the term for FZ. So we substitute that here. So we get this term for the FR value. So now we essentially have used blade element theory to get all these terms for the forces or the section forces in forward flight. And the important thing to remember is that if we look at any of these expressions, these are going to be time dependent terms or terms which depend on psi. For example, here if we look at this equation, ut, up are all functions of r and psi in a general sense, and also theta is a function of psi, beta is also a function of psi. So essentially these are time dependent periodic forcing, and these need to be captured in the solution of the differential equation. So of course mathematically speaking we can simply say this is a function of radial location and time being psi here. So we always use psi in terms of time for periodic problems. So we'll end today here. Now we have used the blade element theory to obtain the expressions as far as the different forces are concerned. And so now we are ready to calculate the rotor forces and some of the main loads. I'll see you in my next video.